Okay, so welcome to lecture number 2 of analog electronic circuits. So first we will start with the revision of what we have done last time, the diode models, and then we'll move on to the diode application, that is the clipper circuits. So does anyone remember about any of the diode models which we have discussed in the class last time? What was the name of the first model? Those were the second and third. The first model was exponential model, right? Exponential diode model. All right. So here, this is the characteristics of a diode. Plus minus VD, and current flowing through the diode in only in one direction. This is anode, this is cathode. I hope it is visible. Yeah. This is current flowing through the diode and the voltage applied across the diode. So this was the exponential characteristics. And what was the relation between ID and VD? They were related. Can I say ID was a function of VD, but this function of VD was non-linear because this curve is non-linear curve. Okay, I guess you know the relation between them, right? ID was proportional to exponential of VD. We have seen that before. All right. So that means it is a non-linear. And when we use this directly the model in your numerical analysis, it will lead to a differential equation, which will be tedious to solve. That's why we go for a approximate model now. The second one was constant voltage model. Okay, what was the constant voltage model saying? That if you have this characteristics, now let me draw it here itself. How it's supposed to look like this, correct? And what was this voltage called as? VD on. Okay, so again I'm redrawing it over here. So this was VD, this was ID, this is how it looked like in zero also, uh, meaning in negative values of VD also. So this was VD on. What is VD on meaning? The on voltage of the diode, the turn on voltage of the diode, after which it starts conducting. So what were the conditions? If the applied voltage VD were greater than VD on, and by the way, this VD on was how much value? 700 to 800 millivolts value. If applied voltage VD is greater than VD on, then the diode D is on. And when it is on, it is replaced with a short circuit and a battery of how much value? VD on. Okay. And if applied voltage VD was less than VD on, then what will happen? The diode is off and it is replaced with a open circuit. Open circuit. This is a short circuit. SC stands for short circuit. I am writing in short form, and OC stands for open circuit. Okay, I guess we have completed the analysis up till here, right? And then after that, what did we say? So basically, this constant voltage model is used in application for 60 to 70% of the cases. And then I think we have also discussed ideal diode model, correct? The third one. So what was the ideal diode model? So if we have this characteristics where Vd is on the x-axis, current flowing through the diode is over here. So this characteristics will look something like this. It will be a line parallel to ID over here like this. So in this case, anything over here, diode was off. Anything beyond this line, diode was on. Over here, if Vd is positive, diode is on. And if Vd is negative, diode is off. As simple as that. So how we can modify the equations? Basically, we can say here Vd on was approximately equal to 0. Agree? Yes or no? So this was 0. So your modified equation is if Vd applied voltage is greater than 0, your diode is on. Yes, diode D is on and it is replaced with a short circuit. No battery required. And if Vd was less than 0, equal to or less than 0, it is diode D is off and it is replaced with a open circuit. Alright, we can say less than or equal to 0. It should be greater than 0 for it to be on. Agree? Everyone? Okay. This is used for, I mean, I've already told you all, this is used for 70 to 80% of the cases and it's fairly approximate value. I mean, approximate model which is fairly used. This ideal diode model is even simpler, but is used for around 5 to 10% cases for quick calculations. Alright, it's not a very good approximate model, okay? So, ideal diode, see basically ideal diode passes positive voltage and blocks negative voltages, we can say intuitively, because it is passing positive voltages and blocking negative voltages. So this is the ideal diode model. Alright, so with this in mind, we'll move ahead and yeah, we'll see some observations. Everything, I mean, so far whatever we have discussed is clear. Any queries here? Alright, so we'll start, before starting with clipper circuits, we'll go through some observations. Observation number 1. So if I have a circuit with a resistor and a voltage source, positive here, negative here, this voltage source is Vx. So the current flowing through the circuit will be Ix. Alright. And if Vx is varied between minus infinity to plus infinity, okay, and this value of R is resistance is R1. Now, if I want to plot Vx versus Ix, can you help me to plot this Vx versus Ix plot? How it will be? Yes. How the plot will be? Anyone? What is the relation between current and a voltage? Will it follow Ohm's law? Yes, V is equal to IR. So what will happen? V is proportional to I, where the proportionality constant is R. So let me know how the graph will look like. It will be a line passing through the origin. Yes or no? A straight line like this with an angle of 45 degrees. Here this is 90 degree, right? This is 45 degrees line. And same over here also. Why over here? Because it's going from minus infinity to plus infinity. So this will go on continuing. Agree? What will be the slope of this straight line? You have studied now in your mathematics. Straight line equation is mx plus c. Yes or no? Correct or no, students? So your y-intercept is 0. So what is y, what is x? Your y is I, x. X is vx. And what is m? M is 1 upon r. Yes or no? That's how we can write now. Vx is equal to ir. So m is the slope. What is m over here? 1 upon r. So how do you determine the slope? This is the slope over here. The slope. The slope is 1 upon r1. Agree? Yes or no? So this Ix is Vx upon r1. Now tell me, if my value of r1 is small, where will the graph go? Will it go closer to Ix over here or closer to Vx? Come on. Yes, of course. So there, this line will be closer to Ix like this. So this is r1 smaller. Okay. Whereas if you have a very large value, so it will be almost parallel to the Ix line if r1 is very very small, almost a vertical line. Agree? Yes or no? So if r1 is very very large, where it will go? Or other way around, right? It will almost be parallel to x-axis, correct? So this is what it is meaning by r1 value. I hope you are following this. If r1 is large, this is r1 is very very large, it will be a line almost parallel to x-axis. And if r1 is small, it will be a line passing to the origin parallel to y-axis. Agree? Understood or this or no? Yeah. Okay. So now let us just tweak a little bit over here and do some slight modification in the same circuit. So let's say again you have a resistor, then you have a battery VB. Okay, you have plus minus Vx R1, and this is plus minus Vp. So how will be the current flowing over here? Yeah, sorry, the polarity over here was different. Okay, tell me, the current flowing will be like this. Now what is the equation of Vx? Can you tell me by simple KVL? Can I say Vx will be equal to Ix R1 plus VB? Do you agree on this? You apply KVL, you will get this only. You want to apply KVL, you can do that. So what is Ix now? Vx minus VB upon R1. Agree, yes or no? And can I say in this equation, for this equation, whenever Vx is equal to VB, my Ix will be 0? Yeah? Yes or no? Now in this situation, I want to plot Ix versus Vx. So help me plot this. Okay, tell me how it will be. When Vx is equal to Vb, Ix is 0. When is Ix 0? So let's say this Vb is a positive number, right? So here it is Vb. Here, this is Vb. So when Vx is equal to Vb, Ix is 0. Now what will happen? So basically, whatever happened over here, same thing will happen over here. It will be a line passing through. Now Vb is the new origin. Yes or no? So the graph will look something like this. This is the same line. Only thing is the origin is shifted to VB. Are you agreeing? And what will be the slope of this line? Again 1 upon R1. So basically what happens is the overall the characteristics is shifted right when a battery is added in series with a resistor. Okay, and when if you increase the value of R1, what will happen to it? Or it will decrease the value of R1, what will happen to it? The slope will, it will go like this. Yes, so this is R1 small, and if you increase the value of R1, then it will decrease. So it as if it is acting like a VB is the origin, and then we are plotting this graph. Okay, so we can write over here. Overall, you can draw the graph. Overall, the characteristics is shifted right when a battery means we are talking about DC battery is added in series with register. Agree on this? Okay, are you following? Yeah, okay, very good. Okay, now let me go back to the first case. So when R1 was smaller, what was the slope happening? Slope is getting larger or slope is getting very small? In this case, slope is moving towards infinite value or a very low value? Yes. And here, when R1 was very large, slope was becoming 0. Okay. So with these observations, we will now start with the clipper circuit. So are you all ready? Observation 1 and 2. Yeah. So let us start with clipper circuits. So this circuit will be called as clipper number 1. Okay. So for the circuit given below, plot the voltage transfer characteristics. So we need to plot VTC curve. VTC is called as voltage transfer characteristics and input output waveform. We should plot VTC curve and input output waveforms. So let me just, since we are writing it for the first time, VTC stands for voltage transfer characteristics. All right. And this is a curve of, let's say if Vx is the input and Ix, oh sorry, v, Vin is the input and Vout is the output. So basically it's a graph of Vin versus Vout, since you're hearing it for the first time. Okay. And what about the input output waveform? The input output waveform will be input versus time, output versus time. So over here you will be plotting x-axis will be time, this will be input, and here x-axis will be time, this will be output. So this characteristics we have to plot, number 1 and number 2. Voltage transfer characteristics will be uh, input versus output, and input output waveforms will be with respect to time. Understood? Yeah. Now can we start now with the clipper circuits? Everyone please. Okay. Now actually we have to follow both the models, but I will teach you only constant voltage model. Whereas for y'all, for exercise, ideal diode model you have to do on your own. What you need to do, if you want to change from constant voltage model to ideal diode model, just make VD on equal to 0. That's it. So that I won't be doing it. You have to do it on your own. I'll be only following the um, constant voltage model. So let us start with the first circuit. So please draw the circuit. So this is plus minus V in. We have a resistor and we have a diode connected over here. And this is V out. Okay. Between positive and negative we have V out. This is R1. Let me mark the current as Ix, and the voltage across the diode D1 is VD1, and this is ground. Okay. Okay. Can we uh, yeah. So the first assumption we write over here is assume constant voltage model for diode D1. And how much voltage you can assume? You assume VD on, which is same as VD1 over here, as how much? 0.7 volt. Alright. Okay. Agree? Now, first you should apply KVL in this loop. So when you apply KVL in this loop, what do we get? You can apply it like this. So what does the KVL says? Plus V in, right? Then come on, tell me the equation. Minus IXR1, then minus VD1, na? Minus VD1 is equal to 0. So we can rewrite it as V in is equal to IXR1 plus VD1. Agree? Yes or no? So here we can write for input voltages less than VD on or less than VD1. Can I say current Ix is 0? Whenever input is less than VD1, my current Ix is 0. So diode D1 is off. Yes or no? Okay. So in this case, if Ix is 0, what is V in equal to? Yes. So what will be my circuit now? Diode is off. So how will I draw it? It is off. Alright. This is plus minus VD1. This is V in and this is R1. So plus minus VD1 is same as your V out. Yes or no? So the circuit reduces to this network, open circuit. Now is it visible? Since this is an open circuit, no current flows through resistor R1. So the voltage across the diode is same as V in. Agree to this? Yes or no? Okay. Now, in the second case, this is the first case. In the second case, if V in is greater than VD1 or VD on, what will happen? The diode D1 is on and current IX flows in the circuit. So how will the circuit will be now? How will be the circuit looking like if I want to draw it? So basically see, this is equal to V out only. Yeah? This voltage is actually diode is connected in parallel, so V out is always equal to VD1 only over here. Okay. So when V in is greater than VD1, what will happen? How does the circuit reduces to? So I have V in R1. When the diode is on, it is replaced with, can you tell me? No, short circuit and a battery. Battery is how much? VD on. Yes or no? And here comes the output. This is V out. And will the current flow in the circuit? Yes, definitely yes. So this is Ix. We are not interested in the current because we are not plotting it. Now can you tell me what will be V out? Same as VD on, no? V out is same as, come on, tell me. VD on, right? Yes or no? Alright. And here, in first case, since V in is equal to VD1, which is equal to V out, right? So can I say V in was equal to V out? Yes or no? In second case, we don't have a relation between V in and V out directly. V out is just equal to VD on. Alright. So now we will plot the transfer characteristics for both the cases now. So please be careful, listen to it carefully. So how to draw it the transfer characteristics for this? Let me draw it over here. Okay. So this will be V in, this will be V out on the y axis. Now tell me how to plot it. What do you mean? Yeah, first of all, I will mark VD on the positive side over here, somewhere around here. I know it may be zero point 0.7, I can write it also 0.7, that's fine. So tell me what will happen. Here two conditions are there. When V in is less than VD1 or VD on, we can say. what will happen? V in is equal to V out. Correct? How do you represent V in equal to V out? Yeah. Till where it will stop? No. See, here, this is the condition. Let me highlight it. Yeah, yeah, yeah. So what I will do is, I'll draw this line like this. So when is V in less than VD on? Up till here, right? So I will draw a line like this. See this line carefully now. 45-degree line passing through the origin. Where it will stop? It will stop here. Agree? Yes or no? Because here the slope will be 1 only, na? Because here this line represents V out equal to V in. When will be Y equal to X? Y is equal to mx, where m is equal to 1. The slope of this line will be 1. Agree? Yes or no? Straight line passing through the origin. Now in second case, what will happen? What will happen beyond when V in is greater than VD1? What will happen then? Then what is V out equal to? Yes, and what is a VD on? See, if this is VD on, is this VD on also? Yes. Correct, na? So it will be remaining constant throughout. See, it will remain constant like this. Agree now? Like this. So this is my VTC curve. Or so again I revise. When V in is less than VD on, V in is equal to V out is equal to V in, and when V in is greater than VD on, my output is equal to VD on itself. Okay. So if the input voltage V in changes, output voltage follows the change in the input voltage up to a certain point, that is VD on, and then the output will saturate or limit to a constant value. Yes or no? And then constant value is VD on. Alright. Therefore the circuit name is also called as limiter. So what is an application of such a circuit? It can be used in Bluetooth receivers. That is the application of such a circuit. Alright. So have you understood how we have drawn this VTC curve? Everyone? Yes. This one. What you didn't understand about VD on? See, what is output? This did you understand? When V in is greater than VD1, output is equal to VD on. Where is output and VD on same, right? And how much is VD on? So, in the output, you draw zero point 0.7 over here. Instead of VD on, I'll write zero point 0.7. Does it mean the same? So, output will be equal to zero point 0.7 only throughout. So, that is why I have constant line. Only in this case, you are getting confused because here also there is VD on and here also there is VD on. That's why probably. See what it is saying is instead of VD on if I write zero point 0.7. Now it is clear. So how will you draw zero point 0.7? You take up, go up, mark till 0.7 and don't draw a straight line. So it is saying when V in is greater than VD1, that is the VD1 voltage, then my output will remain stay at 0.7 volts. It is staying at 0.7 volts or saturated at 0.7 volts. Now did you understand? Okay. Now we will draw. This was the VTC curve. Any other students have any doubt in this? Hello students. Any doubt over here? Yes, no, what? Okay, this was VTC curve. Now we will plot V in versus time and V out versus time. Okay, so I'll go back to a new page. I'll be plotting input output characteristics. Input output. For the first circuit, I'm going pretty slow. Okay, so what is my circuit? Let me redraw my circuit. So this is V in. I have a resistor over here. I think this was the circuit, right? Yes or no? This was D1 and this was R1. Okay. Now you have to write only two conditions. You have to write when the diode D1 is off. Can you tell me when is the diode D1 is off? D1 is off for V in less than VD on. Yes or no? Hello? Yeah. And in this case, what will be my, I mean, if I draw the circuit diagram when it is off, it will be like this. Let me draw it quickly again. I've done it before, but it will be a practice. When the diode is off. Now tell me what will be V out. Can I say here V out will be equal to V in? So V out equal to V in. Can I make a statement output follows the input? Output follows the input. Okay. Now second case, diode D1 is on. What is the condition for diode D1 to be on? For V in greater than VD on. Yes or no? So for this case also I need to draw the circuit, equivalent circuit. How will it look like? So for this case, what is my circuit like? Diode D1 is on. So I'll replace the diode with a battery and a short circuit. Now if I measure output V out, what it will be equal to? Tell me. Tell me what is V out now? No, no, V out is equal to VD on. So V out is equal to VD on. Okay. So output is constant. Equal to point 0.7 or VD on voltages. Now here we are assuming input to be a sinusoidal voltage. Okay. So what? How do you represent mathematically sinusoidal voltage? Anyone? V in is equal to, I want to write sinusoidal voltage. Vm sin omega t, where Vm is the amplitude, omega is the angular frequency. Yes or no? Hello, hello, hello. Yeah. So this is t. We can write omega t also. This is V in. Now here I'll write 0, pi, 2 pi, 3 pi. Always draw input as a dotted line for clipper circuits. For clamper circuits also, whatever the waveform is given, just draw it like a dotted line input. Okay, sinusoidal signal whose amplitude is Vm. What about the negative amplitude? Minus Vm. Agree? So this dotted line is my input, V in of t. Agree? Okay. Now I want to plot V out. So V out I'll plot blue in blue color. V out. So how will it V out will be? See, where will I show VD on line? VD on I'll show positive, right? Over here. red color. Let me show it to you. Here it is. Let's say here it is VD on, or let me write 0.7 volt only. We assume that VD on is 0.7. Now tell me, let me draw this a small straight line, dotted line. Now tell me, when is V in less than VD on? Tell me this case where it is. Whenever is V in, when is V in less than 0.7 volt? In the graph, just highlight the point. Can you tell me where it is less than? Arey, come on. Can you see this bifurcation line, red line? Correct. So above this red line, V in is greater than zero point 0.7, right? Yes or no? Come on, students. It is greater than zero point 0.7, and below this red line, including negative, V in is less than zero point 0.7. Yes or no? Now see the condition. When V in is less than 0.7 volt, my output follows the input. Yes or no? Correct, correct. Come on, say yes or no. So I have to plot the output waveform same as input. So how it will be? Let me draw it a little thicker. Okay. So I'll follow the this thing like this. Input as it is here also. Up till here, boundary. Agree? And what will happen when V in is greater than this thing? Zero point 0.7 volt. Output will remain at zero point 0.7, right? See this. Output will be equal to zero point 0.7. So when input is going beyond that, output is staying at zero point 0.7 volt. See, agree to this. So which part of the output waveform is getting clipped? Nay, that is called as positive part of waveform, right? Positive part of the waveform is clipped. Can I say that? Yes or no? And this dashed line is my V out. I mean this blue color curve, V out of T. So this is clipper number one. Can you tell me what will be the name of such a circuit? It's called as, anyone? Which part is getting clipped away? Yeah, so it's called as a positive clipper. Okay, got the name. If negative part was getting clipped, it would have called this as a negative clipper. Understood this? Understood how the circuit works and how to plot the input output waveforms? Any questions? See, everything, all the explanation is in front of you. If you have any doubt, you can ask just now. So therefore the name clipper, because it clips a portion of a waveform. So here it is clipping the positive part of the waveform. That's why it's called as a positive clipper. So let's write down till then, till the time you have any doubt. Let's write down the definition of a clipper circuit. So write down, everyone. Clippers. So clippers are networks that employ diodes to clip away a portion of an input signal without distorting the remaining part. Clippers are networks that employ diodes to clip away a portion of an input signal without distorting the remaining part of the applied waveform. Okay, all right. You know, it has another name. It's called as a parallel positive clipper. What it is called as? Parallel. You know why parallel? Because no, 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 no. Because the reason is the diode is connected in parallel with the output. Okay, and why the positive clipper? Because positive portion of the output waveform is getting clipped. Understood why it is called as a parallel positive clipper now? First of all, the diode is connected in parallel with the output, and the positive portion of the output is getting clipped. Okay, all right. Now, okay, uh, you need to repeat this as a home assignment using ideal diode model. What will be the difference? Ideal diode model. What will be the difference? Everywhere, whatever you have done, just make VD on equal to 0 at the end. Agree or no? Hello, students. So I am not going to do that. So just a hint, what will be the circuit looking like over here in this case? Yeah. Okay. How it will look like this, and it will be 0, right? Agree. Just make VD on equal to 0. That's it. So this will be the waveform. Explanation wise, everything will remain same. Acha, what about this waveform? How it will be? Anyone? Perfect. So here it will be like this. Agree? Because VD on has become 0 now. So I'm not going to explain ideal diode model because I've already explained constant voltage. Just make VD on equal to 0. So this is VD on equal to 0 volt. So once you have achieved this, making VD on equal to 0 will be very easy, right? But all the practical circuits will have VD on, maybe equal to zero point 0.4, zero point 0.5 or zero point 0.7. Okay, so explaining one circuit should be enough to explain all remaining circuits because the analysis will remain almost same, but I will cover most of them definitely. So if you have any doubts you can ask, or else we have not done with the topic. We have to cover one more clipper circuits today. Actually I wanted to show you all in simulation, that's why I'm waiting. So I have my simulations over here. Clipper circuit number one, a clamper it is. So we can do it in LTspice also. I think this is the same circuit over here, right? So let me plot input output waveforms for this. So this is input waveform and this is output waveform. Can you see this circuit? Same na? Arey, come on, yes or no? See, this is 0, right? So it is clipping a positive part of it. The blue color waveform is my output, black color is my input. Okay, Vx is actually input over here. You can see Vx is input, and it's clipping at around here. The voltage is 651 millivolt. Can you read this part? 651. So yeah, somewhere around 650. See, practical circuits, diode to diode, it may vary also. So maybe that range will change from 600 to 800 millivolt. Agree on this? Understood? And it will repeat for every half cycle automatically. That is what I mean to say. Okay, so this is the way you can check the waveforms over here in LTspice. It will give perfect results. You can verify each and every circuit like this. Now if I want to plot V in versus V out, what I will do is I'll delete this, and here I'll plot V of Vx. See this graph, what it resembles, this only na? Correct? Is it exactly the same, right? See, it passing to the 0, then it going towards. Now this small variation is there because of the actual diode. There will be some difference. There is not sharp transition. It's a smooth transition happening over here. So practically this doesn't happen sharp. This happens smoothly. All right. Okay. Any queries? So this I'll teach you separately how to do it. Now I have one question. How to decide the value of R1? Here I've taken 1K. So how to decide this value of R1? Anyone has any idea? If you're practically selecting the circuit, how to decide the value of R1? Anyone? Write down somewhere. The value of R1 should be selected higher than on-state resistance R on of diode. You will say, what is this? See, when the diode is on, it lot of current flows through it, right? So there is something called as on-state resistance of the diode. So maybe this value of resistance is around 2 to 10 ohms. It's just an example which I'm giving. So select R1 which is very much greater than that. If you select as a 1 kilo ohm, then it will be safer. Okay, so that the diode doesn't charge in, the diode charges instantly. So this R1 value should be greater than it. So this you keep in mind. Value of R1 should be greater than the on-state resistance of the diode. Got it? When the diode is off, the off-state resistance is extremely large. Okay, so this is all about the clipper 1 circuit. Can I go to clipper number 2? Okay, so this before that I'll be discussing about the types of clipper circuits. So please write down the types of clipper circuits which we have. Uh, Sometimes they ask you in the exam types of clipper. Okay, let me reconnect my writing pad once. Yeah. So the first types of clipper circuits can be classified based on the which portion of the output waveform is getting clipped. So first will be positive clipper, then we have negative clipper. In a negative clipper, which portion will be clipped? Negative portion of the output waveform will be clipped, correct? Then it is based on how the diode is connected with the output. So if the diode is connected in series, it is called as a, just writing pad is a little slow. Okay, then it is called as a series clipper. If the diode is connected in series with the output, then it is called as a series clipper. If diode is connected in parallel with the output, it is called as a parallel clipper. Okay, it is called as a parallel clipper. And there is another type. Uh, if you add a battery to a circuit, let's say positive clipper you connect a battery, negative clipper you connect an external battery, a DC battery. Okay, so it is called as a biased clipper. So you can have all the variations over here: positive bias clipper, negative bias clipper, then we have a series positive bias clipper. All the variations are there. So bias voltage is added in series with the diode or a resistor, so adjust the clipping level. Okay, so let's say over here in the circuit, I don't want zero point 0.7, I want 1.7. So what I will do, I'll add a add a battery in series with the resistor or the diode, depending upon it. Okay, so I want, this is my clipping level. This red color line is actually called as a clipping level. This is called as a clipping level. Okay, so to adjust the clipping level, we can add a battery to it. That is called as a bias clipper. Then we have a two level clipper, the last category, or a combinational clipper. So we can call it as a two level clipper. So here both positive and a negative portion of the waveform will be clipped. So it's for something example as this. So if I have a waveform, input waveform, which is looking like this versus time, it will clip both positive and negative portion of the output. Okay, so this is my V out. Got it? So positive clipper, negative clipper, series clipper, parallel clipper, bias clipper to add a DC bias either to the series of the diode or resistor. Okay, and then we have a two level clipper where both positive and a negative portion of the waveform is getting clipped. Okay, students, here, hello. All right. So now we move on to second clipper circuit. So write down clipper number 2. This clipper number 2, just draw the circuit along with me. So we have plus minus V in, resistor R1, same circuit, but with one change. We have a bias circuit now. We have a battery connected. Okay, and this is my output. So this is the last circuit which we are going to discuss today. So this is V out. And we need to plot what all things for this circuitry. This diode D1 and this battery voltage is VB. Let's say that the voltage across VD on, this voltage VD1 is zero point 0.7 volt and this battery is 1 volt, let's say. So VB is 1 volt and VD1 is zero point 0.7, or VD on we can say, which is equal to VD on, the on state voltage of the diode when it is on. All right. So yeah, let us start. So what we need to do, we need to plot VTC curve first. What is VTC curve? Yeah. Hello. Eh. Oh. Voltage transfer characteristics. Please remember it. And input output waveforms. Input versus time, output versus time. So what's the first thing we do? Well, we solve this. Let me close this. Yeah. What's the first thing we do? Assume constant voltage model. Okay. So we write, we assume diode D1 with a constant voltage model. All right. Agree? So let us quickly do the analysis for this now. All right. Let me know now. Tell me. Yeah, I mean, you can do that, but there is another technique. Now, you tell me this 1 volt is helping the diode forward bias, or not helping or it is putting some barrier to the diode becoming forward bias. Tell me. See how it is possible, because this is cathode. Cathode is connected to the positive, so it is not helping. Actually, it is opposing the diode to turn on. Yes or no? So this V in has to overcome this zero point 0.7 volts plus this 1 volt. Agree or no on this? What I mean to say, earlier we used to write na V in should be greater than or less than VD on. But now we have a bias voltage, this VB also. So first check whether this bias voltage is assisting the diode to turn on or opposing the diode to turn on. What about this VB now? The way it is connected, is it opposing or assisting? So opposing means V in has to overcome this voltage also. This plus this. Correct? So the new condition is, are you understanding? Yeah, it's V in less than, the first condition will be V in less than VD on plus VB, and the second condition will be V in greater than VD on plus VB. So this is the boundary. We know what is this number basically. Can you tell me? 1.7 volt. Yes, exactly. So I don't told you, just the clipping level is getting increased. Earlier the clipping level was zero point 0.7. Now it will become how much? Exactly. So it's the same circuit. Everything is remaining the same. Only thing is this will become 1.7 now. And this will also become 1.7. This will increase from zero point 0.7 to 1.7. Rest entire waveform will remain the same. Let us draw that again. No problem at all. So tell me, what will happen if V in is less than this number? Diode is off, right? Yeah. We coming to it. Don't be in a hurry. So here, diode is off means circuit will reduce to, will redraw the circuit. No, don't worry. Here it is. So there will be a resistor. Diode will be replaced with a open circuit, right? Okay. Now tell me what will be the voltage over here. This is VB. This is R1. This is V in. What is output voltage? Come on. Arey, this is open circuit, right? It cannot be equal to VB. No current flows to resistor. So V in is equal to V out is equal to V in, right? So V in is less than VD on plus VB. This thing remains the same. Output follows the input. Yes, agree. So here we can say V out is equal to V in. Now, what about the second case? Let's draw it. So in the second case, we can say diode D1 is on. Diode D1 will be on when V in is greater than 1.7 volt or VD on plus VB volt. Okay. So how does the diode circuit reduces to? There is no harm in drawing the circuit again in exam also. So be careful. A battery will come over here, right? Which is, what is that battery name? VD on. And another battery is there. Yes or no? Yes, VB. I told you what will happen earlier only. But still we are doing it for our analysis. So what will be V out? Tell me now. Will this voltage get added? Yes or no? Huh? Yeah. What will be V out? VD on. Huh? So numerically, what is the number? Zero point 0.7 plus 1. Exactly. Exactly. That's what I was saying from the start. That is just increases or decreases the biasing level. So V out is equal to VD on plus VB. That's it. Now you have to draw the waveform. You see, this is one part. Understanding is one part and drawing is another part. So now help me draw this. Now I'll draw both together. I'll not draw it separately analysis. I'll draw both together. So now help me out in this. Upper side I'll draw the VTC curve. So you only tell me now how to go ahead. So this is my V in. This is my V out. What should I do? What should I mark? Yeah, I mean, if I keep it generalized, can I say it's VD on plus VB? I know it's 1.7, but here also. Here also I'll keep it ready, right? Here it is, I'll write 1.7 volt. Okay. And here there is a barrier to it. Okay. So when V in is less than VD on plus VB, diode is, come on, here it is, off. And what will happen? V in is equal to V out is equal to V in. So you have a straight line passing through the origin, and where it will stop? Here. Okay. So this is the boundary. So this side to the line V in is less than VD on plus VB. This side V in is greater than VD on plus VB. So when V in is greater than VD on plus VB, diode is on and output is stuck at, output is saturates at how much voltage? VD on plus VB. So how much is that? Exactly. This is the graph. 1.7. Understood this? So this is my VTC curve. Isn't it easy? Now that we have done in detail the first circuit. Yes or no? Perfectly clear, crystal clear. Any doubts? Okay. Now, same thing I'll do with input output waveform. So please concentrate over here. Here, let me just shift this focus over here a little. I am drawing. So input output waveform, you draw it like this only. First you draw the dotted line, which is my input signal. And then over it, you draw the output curve. No need to draw it separately. You can draw it separately also, but it's advisable to do it this way. V in of time. This can be V in and V out both. Now, and what is V in actually given by mathematically? Can you tell me? V in is, Are Baba, Vm sin omega t. That's what I'm asking. Correct, na? Sinusoidal signal, na? V in. Input output waveform. Now tell me what will I do? First of all, I'll mark that level. VD on plus VB. So where it will come positive side, right? Year over year. Correct? So I'll mark this level. So let's say how much is that level? This is, what is this level called as? Clipping level. So this is VD on plus VB. This is called as a clipping level. So about this, V in is greater than 1.7 volt. Example. Let's say this is 1.7 volt. And below this, what happens? V in is less than 1.7 volt. Now tell me what will happen. V in is greater than V in is less than 1.7 volt. What happens? Output follows the input. Agree? Are you yes or no? So if V in is less than 1.7, output follows the input. So here it is. This way. It will follow the input. Make it dash line like this. And what will happen if V in tries to go beyond 1.7? Output is equal to 1.7. Yes or no? If V in becomes greater than 1.7, then output is equal to 1.7 now. So output stays over here like this. So this is the graph. I hope it is clear. This is how the graphs look like. So what has happened by adding the battery? The clipping level has changed. Earlier it was 0.7, now it has become 1.7. Example, what I'm telling you. So this is how the waveform will look like. Agree? And this is input output characteristics. So this will be V out of T. What is the name of this circuit? Can anyone tell me? Is it a positive or a negative clipper? Is it a parallel clipper? Is it a biased clipper? So it's a biased parallel positive clipper. What is the name? Biased parallel. Why parallel? Because diode is connected in parallel with the output. Biased parallel positive because it's clipping the positive part of the waveform. So biased parallel positive clipper, or we can call it a yeah, biased parallel positive clipper is the right name. All right, students, is it clear now? If I'm going too fast, too slow, please let me know, or this is fine. Let me show you the in LTspice simulation. I'll teach you this how to use this. So here also, if you see, here also I've added 1 volt battery. Now if I simulate this, let me observe the waveforms now. See, same as what we have got over here, right? Wait a second. Okay, let me simulate this. I'll show you live. Here it is input and here it is output. See this, exactly same as this. So here it will be VB1 plus this volt. So this is 0. As you can see, it's clipping the level. Remember, input is here, it is 5 volt considered. So that's why this level difference is there. Don't worry about it. So this will be around 1.67. See, close to 1.7, what we have discussed. Okay. And negative half cycle, it's following everything. Are you following this? And what about the voltage transfer characteristics? Let me plot it. V of Vx. Okay, here it has called input. Okay, V of. I'll teach you this how to do that. You have practicals. Here it is. See, similar graph. Yeah, this was the one. So this is how you can, build up the circuit in LTspice and get your input-output waveform and the VTC curve. So you have understood what does a clipper circuit do? It either clips a positive part of a signal or a negative part. And what do you mean by voltage transfer characteristics? What is the definition of a clipper? What are the types of clipper circuits? We have done 2 circuits. We have 11 more to go. That we will cover on Friday's lecture. So for today, that is all we have. If you have any queries, you can ask.